This is a presentation of the talk given in Open Compute project session. This includes the slides as well and an explanation that ties up to the operations and uh, operations of the protocol that I'm going to be talking about and the slides. So this talk is all about how do we handle the growing AI concerns. With the explosive growth of AI, we know the demands that are being imposed on not only the AI models, algorithms, etc., but also on data center networks and the internet. So this talk focuses primarily on the overload and data center networks because there is this huge problem with the sustainability concerns with data centers that are having growing energy needs because of the advent of AI. So the agenda for this talk is going to be something like this. We'll briefly look at what is happening with the AI growth and what are the challenges that we are facing in terms of scaling computing and sustainability, plus a few other challenges are there. The major focus is on supporting distributed AI, that is large-scale AI infrastructures, and what are the challenges faced by these infrastructures as they try to host AI. So again, zooming into the main theme of this talk is data centers and data center networks and the underlying technologies used in data center networks to support AI. The goals of our project were very straightforward. We wanted to simplify the complex operations that you currently notice in data centers and data center networks. And by simplifying these operations, we actually make the data center networks secure and sustainable for AI. So this clean slate or reinventing the data center network comes with several benefits, which we'll talk about at the end. Okay, so why reinvent? So to understand why we really need to reinvent, it is important to understand current DCN communication scenarios. The clean slate IP agnostic solution we'll present after that discussion. And when we talk about a clean slate solution, we have to first validate that it's performing as well as the current solutions. And more importantly, will it work in parallel with the IP-based systems that we have today or any other systems that we have today? And what are the AI benefits? Because this whole talk is about the challenges with the growing AI demands. So in terms of AI benefits, are we going to benefit in terms of computing, maintenance, management, security, because we are not going to use IP in our networks? And how about the troubleshooting? The benefits are several. Okay. Last but not the least, from an industry perspective, what is important is the technology readiness of this project. Okay. And when we talk about these sort of new solutions, especially with the growth of AI, there are these two technologies out there, the more popular ones like InfiniBand and Rocky. So is the project that we are proposing, is it yet another? And after we are done with all that, where are we headed with this project next? So looking at AI growth and challenges, AI demands are forcing key architectural shift in the communications paradigm. And that is what you will see when you're looking at InfiniBand and Rocky. And these architectural shifts are necessary to accommodate for the collective communications traffic patterns, the distributed processing of jobs across millions of servers, fast and reliable data movement between servers, networks, highly reduced downtime and latency, and the extensive amount of configuration management, maintenance, troubleshooting overload that we are currently facing. Okay. There is a heavy dependence on how networks operate and the network performance, which actually leads to the network technologies. So, to address all the above concerns that I have listed here and the needs, you will notice that this is supported by the network, and we have to look into the network performance, which in turn is dependent on the network technologies because they are the ones that are going to be moving the data. And who is moving the data? The data movement is controlled by network protocols. So the focus of this topic is more on data center network protocols. Coming to the distributed and large-scale AI infrastructure, what is the role of data centers, data center networks, and the internet to support AI? They are the ones that are moving data across massive collections of network servers. Okay. So what is the problem then? The problem is that the network protocols that we are using, whether in the internet or whether in the data center networks, they are all decades old and were designed for networks and technologies of that era and have been retrofitted repeatedly to address our current needs. And if there is a need for a specific functionality, we add another protocol. And this way we have sort of developed a very highly complex protocol system. Consequence, there is this escalating operational complexity. Along with the operational complexity comes maintenance, management, and troubleshooting effort. How about the downtime? They get adversely impacted. There is a performance degradation with scale, which would be obvious when I present some result. There is increased hardware and software needs, obviously. Who is going to perform all those operations? It is the hardware and the software, and that in turn leads to escalating energy usage and carbon footprint. How about costs? That is pretty straightforward to figure out. With all this escalating, the costs are also going to be higher. How about IP and security? This is something which we sort of cover up under the hood, saying IP is secure. We overload it with a lot of security mechanisms to make it secure, but IP is inherently not secure. So these are the facts, and we have to justify these facts now, right? So to justify the facts that we just discussed, let us look at IP-based protocols and network performance. More importantly, let us throw some questions here. What were the goals when IP was designed? What were the communications technology at that time? What were the computing limitations? What about the transmission technologies? It was a totally different era. Okay. But the justification that we continuously keep giving is IP is widely deployed and it works. And like I said, what is happening under the hood, many of us don't even want to check it out because it is deployed worldwide. It could be disruptive to change all that. And it is able to support all types of communications. It is working, so let it work. So, can we continue to extend this justification with the advent of AI? It's not so, because with the advent of AI, many of these challenges and limitations are emerging. That's where you're seeing these new approaches surfacing, which are trying to avoid IP and TCP. Using 30-year-old, 30, 40-year-old protocols to move data in today's advanced networks is a bit difficult to accept. Okay, so why reinvent network protocols? Let us look at the recent directions with the advent of AI. Okay, there is the InfiniBand and Rocky. Both of them do not use TCP. And InfiniBand has its own routing fabric extending to servers, failure handling, etc. And this approach already is indicative that there are problems with IP TCP solutions. Okay. So we have to do a rigorous assessment of we are going to do a rigorous assessment of a popular DCN protocol suite to justify why we are reinventing network protocols. And this rigorous assessment is going to be based completely from an operational perspective. We are not going to go into the details. Okay. So, and for this rigorous assessment, we are going to use a popular DCN hyperscale topology, the folded-Clos topology, and the popular protocol suite that runs on folded-Clos topologies. And in the light of the above discussions, we are then going to say, is there a simpler way to achieve these operations? Okay, for which we are using so many protocols, so many functions, so many operations. So if there is a simpler way, what is that? And that is the time we'll introduce you to our project. Okay. So a popular DCN topology and a popular protocol suite. Folded-Clos topology, the picture that just came up, that is a two-pod folded-Clos topology. Just to explain the concept, you have hundreds and thousands of devices in a typical folded-Clos data center network. And this topology has numerous benefits. So in our Clean Slate initiative, we are not attempting to change any of the topology structure because it's very resilient, has got high redundancy and several other benefits. What we are going to be targeting is the protocols that we are going to be running on this topology. Okay. And the most popular protocol suite used in folded-Clos topologies are Border Gateway Protocol for routing, equal cost multipath routing for load balancing, Transport Control Protocol. Because we use BGP, we need TCP. Bidirectional forwarding detection. BGP failure detection is not fast enough. So to improve the uptime, we enable BFD in BGP. And then lastly, we need user datagram protocol because BFD will run on UDP. And to facilitate the operation of all the above protocols, we use the Internet Protocol, which is just a packet forwarding protocol. Okay. Let us look into this rigorous assessment of the DCN protocol stack that I just walked you through. Okay. Start with the Internet Protocol. Okay. It performs packet delivery, forwarding, etc., etc. You can get this piece of information from anywhere. So it does all those operations just to offer generic host-to-host connectivity, which is not what we require to support AI in our networks today. About the complexity, it's primarily because of the ecosystem of protocols required to support IP communications. The next protocol is the Border Gateway Protocol, which is a routing protocol. And again, you can Google it up and it performs all those different operations there. When it comes to computation, it has got an extensive amount of computation that it has to do. And the problem comes up when you try to scale the network. The routing computation grows with the number of network prefixes, available paths, etc., etc. And that leads to significant CPU and memory consumption for continuous route processing. There are several references at the end of these slides. You can check it out. Coming to configuration, again, we all know that BGP requires a lot of configuration for its operation, including the AS numbers, which traditionally was required for inter-AS communications. When it comes to complexity, just look at it. We have to run an eBGP session and extensive ASN assignment. Sorry, the eBGP session has to run between every pair of router that you saw in the folded-Clos topology, connected pairs of routers. And there is an extensive ASN management that is required, adds to the complexity of the operation. To support Border Gateway Protocol, we need Transport Control Protocol, and TCP has been is famous for its complexity in operation. It was a very cool protocol long time ago, and there are several questions raised about its needs anymore. Okay, so those are all the functions that TCP performs, and computations, again, it's computationally intensive, has got a lot of configuration needs because it supports a lot of options. Again, when you're looking at the complexity, high computational complexity, state complexity, and TCP is again maintained. A TCP session is maintained between every pair of device on the network there. Okay, and that is millions of simultaneous TCP connections, especially when you start scaling them to thousands of nodes, that can be a problem. Okay, the next is the equal cost multipath protocol, which performs a few operations. I'm not going to go through them. It requires some amount of configuration, complexity, the hash-based calculations, etc., might add to a little bit of complexity. The troubleshooting could be a problem, but otherwise it's not all that complex. Okay, and instead of using ECMP, which we again took it off the shelf and put it into our protocol stack, a simple hashing algorithm could have been customized to our needs and used efficiently. Okay. Then comes BFD. BFD performs all those functions that just came up. When it comes to operational complexity, again, you're talking about a BFD session between every neighbor. Thousands of BFD sessions, aggressive timers. It's a simple hello protocol, uses aggressive timers to try and speed up the failure detection. Okay, so finally, there is the UDP because BFD requires UDP. Okay, 6 protocols to forward data between servers in a data center network. And these 6 protocols are running in 10,000 plus TORs, thousands of spines. And if you count the number of links which contribute to the sessions, the numerous sessions, TCP, BFD, BGP, etc. session, those are the number of links that we are looking at, so you can understand what would be the scalability challenges. Okay, so why this matters for protocol scaling? Because these protocols require link state monitoring. You need BFD session, TCP session, BGP session, ECMP calculations, failure notifications, which can be pretty extensive. Okay, let us have a quick look at InfiniBand and what they are attempting to do. They are eliminating protocol layers. They use channel adapters for network cards. They use switches to forward packets. They have a subnet manager which assigns addresses, discovers a topology, and computes routes. And the technology extends not only to the network part of it, to the servers as well. They use the global unique ID and a local ID addressing scheme. Whenever there is a failure, they inform the subnet manager and they perform the route update, and that is a centralized sort of system which can be a bottleneck. Ethernet NICs cannot communicate over InfiniBand, and we need IP-OIB for that purpose. And that introduces a few limitations. Okay. ROCE, Remote Direct Memory Access over Converged Ethernet. It is Ethernet based, it uses IP, and often it uses BGP, ECMP, and BFD. It does not reduce the operational complexity. Okay. So, what we are targeting is simplify operations and in the bargain, make your communications secure and sustainable. So we are reinventing the data center network protocols. We are attempting a clean slate approach. But we have taken into consideration that any solution, if it has to be deployed out there, They have to be backward compatible to Ethernet and IP. So our solution is IP agnostic. It can also interwork with current IP Ethernet based data center networks and other deployment. It can operate in a parallel stack. Okay. The goal is of what we are proposing is to solve the routing domain challenges first. And the premise is if you're looking at a data center network, you have the servers, they perform certain operations. You have the routing fabric, which all that it does is routing and load balancing and forwarding traffic, which is communications and transport, whereas the servers are just sending, receiving, and processing the data. Okay. So, and if you look at the scheduler, what you need here is an intelligent scheduler which is able to understand the traffic in the routing fabric and accordingly schedule jobs to the servers so that you make an efficient use of your data center network. And AI workloads, why this approach is important is AI workloads require tighter coordination between computation and network fabric. This can avoid bottlenecks. What you're looking for is a smart job allocation, which is congestion aware. So in this presentation, we are solving the routing domain problem. Okay. The next activity would be to simplify the server operations because to support all these servers, the protocol layers there are also quite complex. And then lastly, we will be targeting an intelligent job scheduler. Okay, let us introduce you to this new protocol, the Clean Slate Protocol, Multi-Route Mesh Tree Protocol, MR-MTP. MR-MTP simplifies route setup and network operations. It is a networking protocol. Okay. So again, if you see on the right side here, that is the same two-port topology, C1, C12, etc. They are the servers. I'm representing them as just one block. Okay. We have a very clear animated VID route establishment in the backup slides. But just to cut down on my presentation time, I'm just going to use a very simplified animation here. So MR-MTP establishes loop-free routes dynamically and it adapts to the connectivity changes. It is self-healing. It doesn't require any route recomputation. And we use a mesh tree algorithm for this purpose. And the mesh tree algorithm was designed to dynamically adapt to connectivity changes, unlike our computer science tree algorithms like spanning tree, Dijkstra tree, etc. So what we are going to do is construct mesh trees, which will be rooted at the TORs. They are the top of rack switches. You see them at the bottom here. Okay. And in terms of configuration, and this is the only configuration we need, we have to identify the devices in our routed domain, okay, to belong to tier 1, tier 2, or tier 3. That is the only configuration that is required. And the TORs are going to now derive a virtual ID. The whole routing system will be set up using virtual IDs. Okay. The TORs will first derive a virtual ID from the subnet address of the server rack. Okay. So that's what you see here. So I'm not explained clearly how this happens. Probably later on I'll be explaining that. So this star got a virtual ID 11, 12, 21, and 22. They were auto-derived from the subnet IP addresses. Auto-assigned virtual IDs will then be used to build the meshed trees, which will be branching off from these stars to the upper tier spines. Okay, So that is the red tree going from TOR 11. It is reaching out to the two connected spines, and they are now given virtual IDs 11.1, 11.2 simply by appending the outgoing port number to the TOR VID. And spines in tier 2 then extend the tree branches to spines in tier 3 by just appending the outgoing port numbers here again, and you'll see they get, so this should have been a port number 1 here, 1 and 2. So 1121, that is the virtual ID for S22. The red tree continues to grow, so just follow it up later on. I will be giving you the animated slide set. Okay, so if you check it out, all those different virtual IDs have established a path from TOR 11 up to the tier 3 spines. Okay. Now let us track a green tree from TOR 21. Okay, so similarly, again, virtual ID assignment, and you see that the green tree has been constructed, and just check it out. The green tree meshes with the red tree. The branches mesh, but no loops will be created because the virtual IDs inherently are loop avoiding. So now let us, for the sake of completion, let us check the blue tree grown from TOR 12. I'm not going to grow the purple tree from TOR 22 because the picture can get very cluttered up. Okay, so if you look at what happened here, just one single slide, just virtual ID growth, and all possible loop-free routes have been established from the TORs to all top tier spines in a distributed manner. Okay, as simple as that. No address assignment, routes are emerging right from the topology. Okay, check the top tier spine VIDs now. Now I have just put up, I have color coded it, and you'll see all top tier spines have a virtual ID from all the TOR, a branch from all the TOR. The VIDs are storing loop-free routes. No routing tables, nothing, just the virtual IDs. They also carry the relative positional information, which is useful in forwarding. So the operations that I just explained in the last two slides, using those MR-MTP replaces BGP, TCP, IP address assignment, ASN assignment, etc. Okay, how about packets that have to be forwarded between C11, C12, etc.? Because they are still IP-based. These are the servers, they are IP-based. So how to forward packets between the servers? For that purpose, the IP packets arriving from the server, when they are picked up by the TOR, they are encapsulated in an MR-MTP header, which has got the source VID and a destination VID. So this is the packet coming from the server C11, and it is destined to go to C21 at TOR 21. This is what I was talking to you about. If you see, the TOR is deriving its virtual ID from the IP subnet address. Okay, so when the packet arrives at TOR 11, the MR-MTP will derive the source TOR VID destination, TOR VID 11 and 21, using the same algorithm, and encapsulate the IP packet in the MR-MTP header. So in this box that just came up, all the forwarding will be done by MR-MTP only. No other protocol is running in the devices in that box. And the only operation required to do routing is routers will compare the destination virtual ID with their neighbor VIDs and forward to the longest substring match, else they will send it to their upper tier parent. Okay. This substring matching is done till the packet reaches the destination TOR, and when it reaches the destination TOR, he checks the destination BID here. He knows it has reached the destination. He will remove the MR-MTP header and deliver it to the servers there. For load balancing, we used the Jenkins algorithm, which can be whose parameters can be tuned. Okay, MR-MTP thus replaces IP and ECMP also. Okay, again we have an animated step-by-step IP packet forwarding in the backup slides. Failure detection and high uptime is very, very important when we consider network performance. So what happens in MR-MTP? In the routing domain, like I said, the only protocol running there is MR-MTP. So all messages are MR-MTP messages. So all messages are keep alive messages. Only if I do not have to send, if I do not have an MR-MTP message for the duration of a hello timer, I will send a 1 byte hello message. Please compare this with BFD's hello messages. And if I miss MR-MTP messages for 1.5 times the hello timer, and that is our dead timer, we will assume the neighbor is down. And this actually cuts down our failure detection time by 50%. Okay. But how are we able to do this, and how are we able to handle route dampening? We handle route dampening by using what is called as a reverse route dampening. And in the case of reverse route dampening, I'm seeing here, we assume a neighbor is up only after I receive 3 consecutive messages from my neighbor. I don't see that mentioned here, but that is the way we take care of reverse route dampening. Okay. And the way MR-MTP handles, you can look at the routing table. There was no global computation, no global dissemination. That is just a local dissemination. So that reduces control plane traffic overhead considerably, and we get very fast recovery and convergence. So that is the protocol stack we use today. Okay, those are the 6 protocols. And this is one very simple protocol that is able to perform all the operations that you see on the protocol, BGP protocol stack today. What are the attributes of MR-MTP? It is IP agnostic. It can work with any layer 3 protocols. It's backward compatible to Ethernet. And to facilitate deployment, you can operate it on a parallel stack with BGP and its suite of protocols. You can turn on MR-MTP and it'll take over the forwarding. You can turn it off and the forwarding will be taken over by BGP. What are the benefits? Obviously, highly reduced computation configuration, reduced computation leading to reduced energy cost, reduced equipment cost, very low maintenance management and troubleshooting. Accordingly, the cost benefit, no IP, security benefits, custom security. You can design customized security solutions based on your data center network needs. Okay, now coming to the performance of this protocol, we do compare it with the standard BGP, ECMP, BFD protocol stack, and we use the Fabric testbed for this purpose. You can check this out. This is supported by National Science Foundation and is spread all over US and has got a lot of resources. You can actually reserve virtual machines in these sites, connect them to the topology that you desire, and that's what you see here. So what does the Fabric testbed provide you? It's a large-scale testbed for distributed system research, user control layer 2, layer 3 networks and topologies. You can do clean slating networking research. And like I said, after setting up all your virtual machines and topologies on the different sites, you can upload your protocol code, execute the code that you want, collect the data, outcomes, logs, Wireshark captures, and compute the performance. Okay. So the advantage of testing on the Fabric testbed is it gives us a TRL6 level prototype validation. Looking into the performance investigation, we used a 4-pod test topology. That's what you see coming up there. So earlier we were showing pod 1, pod 2, pod 3, pod 4. We limited our studies to 4 pods because setting up resources in Fabric takes time. And hence, for the scaled testing, after validating the protocol on Fabric, for the scaled testing, we moved on to mininet.org. Failures were introduced in multiple points. You see TC1, TC2. Those are the failure test cases. And all the Fabric test scripts for testing are available on that GitHub link. Okay, the Mininet testing for scalability is also available on that GitHub link. For eBGP, ECMP, BFD, we downloaded the code from FRR routing. For MR-MTP, we downloaded the code from that GitHub link. Okay. For the performance evaluations, those are the 4 different test cases, as I explained to you in the last slide. And the performance metrics we focused on were convergence time, control plane overhead, traffic overhead, packet loss. And when we talk about packet loss, we looked at the upstream packet loss and when the traffic flowed upstream and when the traffic flowed downstream. So what I mean by that is when the traffic flows from C11 to C44, the failures here are detected earlier. So you will see the performance is slightly different. But when you're sending the traffic from C4 to C11, these failures are detected at the far end quite some time later, and that also impacts the performance. So this is the convergence time. That is convergence time in milliseconds. So that is MR-MTP convergence time down to 100 milliseconds averaged out. And if we don't use BFD, BGP has got a high convergence time, though we set the hello and dead timer to 1 and 4 seconds. So when you introduce BFD, it is reduced considerably. Okay, the BFD hello timer was 300 milliseconds. That is the minimal that we could set in our systems. Okay. So MR-MTP converges approximately 2 to 22 times faster than BGP and 1.6 to 9 times faster than BGP and BFD. The reason 2 to 22 is it depends on the failure test cases. Failures at TC1, TC3, if you see, is lower. Sorry, failure at TC2, TC4 has a lower convergence time compared to failures at TC1 and TC3. And whereas if you look at MR-MTP, it's more consistent across the 4 failure test cases. MR-MTP also exhibits a narrower convergence time from 99 to 125 milliseconds compared to BGP and BFD. So it's a faster, more predictable network recovery. Control plane traffic, again, this is the amount of control plane traffic that we generated. And when you look at BGP, BFD, there's not much difference. That is the control plane traffic that is generated. Actually, we did not count the amount of hello traffic generated by BFD because that is really not part of the recovery traffic. So MR-MTP has an 88% reduction in control plane overhead compared to BGP. And this is a reduction in the computations, reflects a reduction in the computations. Coming to the packet loss, uh, when the traffic is going from C11 to C44 and the failure is happening on the same side as C11, notice MR-MTP has very low packet loss. This compared to, in either case, again, the packet loss is pretty consistent compared to the packet losses that you notice with BGP and BFD. See the vast differences when the test cases changes. MR-MTP packet loss is less by up to 97% relative to BGP, 93% relative to BGP BFD. MR-MTP recovery behavior is consistent and predictable, which is a very important consideration in network performance. Let us look at the configuration overload. That is the configuration required for one BGP router for the four pod topology, and that is the configuration that is required at one MR-MTP router. That is all stored in memory, that's all goes into the computations, so that's a heavy reduction. BGP configuration complexity is proportional to the order of n, MR-MTP is order of 1. 87 to 93% reduction in configuration complexity. How about the memory load? This is just for the storage part of it. This is the routing table in one router for BGP, and that is the routing information that MR-MTP requires in its top tier spine. Reduces forwarding state complexity, cuts down a lot of the operational complexity. So let us look at the AI workloads and DCN directions. So proposed solutions, there are several of them here, but the more popular ones are InfiniBand and Rocky. And when we look at the approaches, the trend towards approaches to solve this demands raised by AI, we are trying to bypass traditional IP TCP stack. We are minimizing software overhead, lossless deterministic fabric, designing of those fabrics, collapsing multiple protocols, co-designing network and workload. So if you look at it, MR-MTP addresses the 1, 2, and 4 of those proposed approaches. All the yes you see there. We are not yet there to design a fabric for this one. And this one, we are working on it. Okay. InfiniBand is, like I said, a very popular approach, a non-IP simplified high performance fabric, which is not backward compatible to IP and has got some server communication challenges if you want your servers to be IP-based. ROC is retrofitted Ethernet for AI demands and does not address protocol complexity. Clean slate MR-MTP collapses multiple protocols into a single topology-aware framework, routing framework for simpler, faster, and more secure data center networking for AI. If we come up with a comparison chart between BGP, ROC, InfiniBand, and MR-MTP, BGP, ECMP, operationally pretty complex. MR-MTP, heavy reduction on the protocols and complexity. Okay, ROCs requires some complex tuning, and MR-MTP does not depend on any of those tuning and Ethernet hacks. InfiniBand, it's expensive and specialized. MR-MTP is generalizable, very simple architecture. Looking at hyperscale networks, they require support for synchronized group-oriented high-volume flows, control plane scalability, continuous resilience with minimal disruption, congestion-aware load balancing, built-in scalable security mechanism, exploit topology for performance and resilience, And all MR-MTP addresses all those tick marked bullet points except the first one. So again, summarizing, eliminates traditional routing tables. It's truly a clean slate approach, uses VID tier-based forwarding, scales very well with topology. The paths are derived from the folded-Clos structure. No global route recomputation, near instant failover convergence for hardware failures at least, minimal configuration, fewer human errors, fewer protocols, no route distribution, no routing protocol, IP agnostic, and all the benefits of being an IP agnostic solution. Okay. So these are some of the challenges MR-MTP is addressing for hyperscale systems. It is replacing the traditional routing protocol-based solutions to topology-aware forwarding, eliminates protocol complexity, uses the folded-Clos structure, virtual IDs, and mesh trees. It's a very scalable, low latency, and with the reduced computation, the routing fabric is going to be highly energy efficient. So what are we looking for in AI native networking? A a networking paradigm where network fabric scheduler distributed AI framework cooperate to optimize data movement. It's data movement for AI workload. Okay. Network that understand the collective communication patterns, workload objectives, and enable efficient routing, load balancing, congestion management, and resource utilization. So, when we look at InfiniBand is able to address all this, but probably a major issue that I foresee here is the centralized subnet manager and scheduler, and it may not be tightly coupled. AI native networking and MR-MTP, topology, structure aware tuning, tunable hash algorithm, congestion awareness can be introduced, job structure, congestion based load handling, which we plan to do it in the future. So if you look at the virtual IDs of the connected server subnets, okay, S1X VID, they are telling you which are the connected server subnets because they are directly close to the subnet. You look at the next level of spines, they tell you the reachable subnet footprint. So S1s tell you the connected server subnets. There's a lot of connectivity information here. Okay, and so on. If you go to S3 and so they have their own map of the virtual IDs carry the map of the topology. Okay, congestion, we plan to do that by monitoring the MR-MTP traffic. So our next target task is to simplify server operations and then add an intelligent job scheduler. So coming to AI native networking and the internet. How about moving AI data over the internet? Enterprise and ISP networks, inter-AS communications, are they AI aware? Can we make them AI aware? We have another project that we are working on called the Expedited Internet Bypass Protocol, which is also topology aware routing, and it simplifies intra-AS operations considerably, and it's been demonstrated to operate an enterprise and ISP autonomous system. Recently, we also extended its testing for inter-AS. We can probably test it out for AI native networking over the internet. So these are certain activities that we are interested in. If anybody is interested in a demo, we can arrange one. If we would like to have some industry collaboration in working on the server protocol stack and the intelligent job scheduler, moving the traffic over the internet, enterprise, ISP networks, and so on. Okay. So here are some concerns, slides worth noticing. These I got it again from an AI support, and this is what is predicted with the growth of AI in the upcoming years. Okay, so in terms of energy growth, capacity explosion, etc., etc., there's it's going to be pretty challenging in the upcoming decade. Okay. So I have pulled out a lot of references for you on the control plane complexity, all the routing protocol, what happens with them, BGP complexity, um, references to studies about the complexity. So here are the animated slides. So when you have time, please check them out. Thank you.